Here is pi, 3.14159, and on and on. The digits keep coming, and they never fall into a repeating pattern. Not after 100 places, not after a billion. Compare that to an ordinary fraction. 1/3 is 0.333 forever, but that is a single digit on loop. 2/7 is a block of 6 digits that repeats without end. Every fraction, every ratio of two whole numbers does this. Sooner or later, its decimal locks into a repeating cycle. So a fraction and a never repeating decimal are two different kinds of animal, which raises the obvious question: is pi secretly a fraction, some enormous ratio of two whole numbers we simply have not found, or is it genuinely not a fraction at all? A number that is a ratio of whole numbers is called rational. A number that is not is called irrational. The claim we are going to prove today is that pi is irrational. There is no fraction, however large its top and bottom, that equals it exactly. You cannot prove something is impossible by searching. There are infinitely many fractions. You will never check them all. So we do the opposite. We assume the thing we want to forbid, and we chase that assumption until it says something absurd. So, for the length of this argument, suppose pi really is a fraction. Suppose you can write it as some whole number a divided by some whole number b, both positive. We do not know what a and b are, and we never will, because in a moment this assumption is going to destroy itself. But grant it for now. Pi equals a over b. Here is the shape of the trap we are going to build. From that single assumption, we will construct one specific number, one honest quantity, and we will prove two things about it that cannot both be true. We will prove it has to be a whole number, 0, or 1, or 2, something with nothing after the decimal point, and we will prove it lies strictly between 0 and 1. A whole number, strictly between 0 and 1. There is no such thing. When the trap snaps shut on that impossibility, the only thing that can give way is the assumption we started from. Everything hangs on one carefully chosen polynomial. Let me just show it to you, and then we will earn every piece of it. We take x to the power n times the quantity a minus b times x, also to the power n, and we divide the whole thing by n factorial. Here a and b are the numerator and denominator from our assumption, and n is a positive whole number, a dial we get to turn. For now, look only at the shape. Between x equals 0 and x equals pi, this thing is a single smooth hump. It is 0 at both ends and positive in between. Why 0 at the ends? At x equals 0, the first factor, x to the n, is 0. And at x equals pi, remember pi is a over b under our assumption. The second factor, a minus b times x, becomes a minus b times a over b, which is a minus a, 0. So the hump is pinned to the floor at both ends, exactly where we want it. That factorial on the bottom will matter enormously later. Keep it in the corner of your eye. For now we have a hump on the interval from 0 to pi, and a dial called n. Now turn the dial. Watch what happens to the hump as n grows. At n equals 1, it is a fat, tall arch. At n equals 2, it is thinner. By n equals 5, it is a low, tight bump hugging the floor. The reason is the factorial. The top of the fraction grows like a power of n, fast, but not that fast. The bottom, n factorial, grows faster than any power. Multiply by 2, then by 3, then by 4, then by 5, and the denominator runs away from the numerator, so the whole hump is squeezed downward, and it keeps getting squeezed, without limit the higher you set n. This is the first of the two jaws. The area trapped under this hump, and in a moment, under a close cousin of it, can be made as small as we like, simply by choosing n large enough. That is going to force our mystery number to be tiny, but tiny is only half the trap. The other half is stranger, and it is where this polynomial earns its keep. This humble little hump is secretly an integer-making machine. Take our polynomial and start differentiating it, slope of the slope of the slope, as many times as you like. Then plug in x equals 0. The claim is that every single one of those numbers is a whole number. Here is why, and it is the point of that factorial. If you multiply out x to the n times a minus b x to the n, you get a polynomial whose coefficients are whole numbers, because a and b are whole numbers. The lowest power of x that appears is x to the n, nothing smaller. Now, when you differentiate a term like some integer times x to the k, and then set x to 0, everything vanishes unless you differentiate it exactly k times. And then what survives is that integer multiplied by k factorial. And every power k in our polynomial is at least n. So the k factorial that appears always contains our n factorial as a factor, which means dividing by n factorial leaves a whole number behind, every time. The factorial on the bottom is not decoration. It is exactly the right size to cancel and turn every derivative at 0 into an integer. So, our little hump, differentiated any number of times and evaluated at 0, always lands on a whole number. We showed the derivatives are whole numbers at 0. We need them to be whole numbers at the other end too, at x equals pi. And here the polynomial hands us a gift. It is perfectly symmetric. Look at the two ends, replace x by pi minus x, and work it through. The factor x to the n becomes pi minus x to the n, and the factor a minus bx, using that pi is a over b, turns into b times x to the n. Multiply them and, after the dust settles, you get back exactly the polynomial you started with. In symbols, f of x equals f of pi minus x. The hump is a mirror image of itself, about its own center. Mirror symmetry is exactly what we need, because the graph near x equals pi is a flipped copy of the graph near x equals 0. The derivatives at pi are just the derivatives at 0, possibly with a sign flip. Same numbers, maybe a minus sign. And a whole number with a minus sign in front is still a whole number. So the conclusion carries across. Differentiate our polynomial as often as you like. Evaluate at 0 or at pi, and you always get an integer. Hold on to that. It is the raw material for the whole number half of the trap. Now we assemble those derivatives into one bookkeeping object. It looks arbitrary for about 10 seconds, and then it clicks. Define a new function, capital F, as an alternating sum. Take our polynomial f, subtract its second derivative, add its fourth derivative, subtract its sixth, and so on. Alternating signs using only the even numbered derivatives until they run out, which they do, because a polynomial differentiated enough times becomes 0. That is capital F. It is built entirely out of derivatives of our hump, each evaluated the same way. Two things follow immediately, and both are free. First, since capital F is just a combination of those derivatives, and every one of them is a whole number at 0 and at pi, capital F itself is a whole number at 0 and at pi. Add and subtract integers, you get an integer. Second, and this is the mechanical heart of the proof, add capital F to its own second derivative, and almost everything cancels in a telescoping cascade. The f double prime from the first piece kills the f double prime from the second, and so on down the line. What is left standing after all the cancellation is just our original hump, f. That identity, capital F plus its second derivative equals f, is the key that unlocks the door, because it lets us write down an exact antiderivative for the one thing we actually care about, our hump multiplied by the sine of x. Consider the expression capital F prime times sine minus capital F times cosine. Differentiate it with the product rule and watch the middle collapse. You get f double prime times sine plus f prime times cosine minus f prime times cosine minus f times the derivative of cosine, which brings back a plus f times sine. The two f prime cosine terms cancel outright. What remains is f double prime times sine plus f times sine. That is, the quantity f double prime plus f all times sine. And we just proved f double prime plus f is exactly f. So the derivative of that tidy expression is precisely f of x times sine of x. In other words, we have found in closed form an antiderivative of our hump times sine. That is a rare and lucky thing, and it is not luck. It is the whole reason capital F was built the way it was. With an exact antiderivative in hand, we can do the one calculation the entire proof has been driving toward. Integrate our hump times sine cleanly from 0 to pi. Here is our mystery number. Take our hump, multiply it by the sine of x, and add up the area under that curve from 0 to pi. Call the result I. Because we have an exact antiderivative, we can evaluate this without any approximation. The area equals our tidy expression, capital F prime times sine minus capital F times cosine, measured at pi, minus its value at 0. Now plug in. At both endpoints, the sine of the angle is 0, so every term carrying a sine simply vanishes. What is left involves the cosine. The cosine of pi is -1, and the cosine of 0 is +1. Push the arithmetic through, and the whole area collapses to capital F at pi plus capital F at 0. Read that off. The area under our curve, this number I, is exactly capital F at pi plus capital F at 0. And we established 2 sections ago that both of those are whole numbers. The sum of 2 whole numbers is a whole number. So I, our mystery area, is an integer for every value of the dial n, no matter how large. That is the first jaw of the trap, locked shut. Whatever this area turns out to be, it has nothing after the decimal point. Now the other jaw. We know the area is a whole number. Let us find out how big it actually is. And the answer is barely bigger than nothing. First, the area is strictly positive. On the open interval between 0 and pi, our hump is positive, and the sine of x is positive too, so their product is positive, and the area under a positive curve is greater than 0. The number I is not 0. Now the upper end. On this interval, our hump never exceeds a certain size, and the sine never exceeds 1. So the area is smaller than the length of the interval times that largest value, a quantity with n factorial sitting in the denominator. And here the factorial finally does its work. Let me show it with small concrete numbers, using 3 in place of pi, just so the sizes are visible on screen. Watch the actual area shrink as we turn the dial. At n equals 1, it is about 3.5. At n equals 3, about 2. At n equals 5, under 1/2. By n equals 8, it is around 1/100th. By n equals 12, it is a few hundred thousandths. Every one of these is a real computed area, and they are plunging towards 0, dragged down by the factorial, exactly as promised. Put the 2 jaws together, and the trap closes. We are free to choose the dial n as large as we please, and the number I stays a whole number the whole time. That never changes. But the area is also strictly positive and shrinking without limit towards 0. So pick n large enough that the area drops below 1. With 3 standing in for pi, that already happens by n equals 6. Now look at what we are holding, a number I that is strictly greater than 0, strictly less than 1, and, at the same time, a whole number. There is no whole number strictly between 0 and 1. 0 is not in the interval, 1 is not in the interval, and there is nothing in between. The 2 facts we proved about I cannot both hold. Something we did was not allowed. And every step after the assumption was airtight. The polynomial, the derivatives, the symmetry, the telescoping, the antiderivative, the bound, each one forced by the one before. The only loose thread, the only thing we merely supposed, was right at the start, that pi could be written as a over b. So that assumption is false. Pi cannot be written as a ratio of 2 whole numbers. Pi is irrational. Step back and look at the machine we just ran. One polynomial, chosen so its factorial makes it tiny, and its integer coefficients make its derivatives whole. One alternating sum that telescopes. One integral forced by an exact antiderivative to be a whole number, and forced by a simple bound to be less than 1. That is the entire argument. Ivan Niven published it in 1947, and on the page it is barely half a page long. No continued fractions, no heavy machinery, just calculus a student meets in a first year. And the same machine barely has to change to prove more. Feed it a slightly different polynomial, and it shows that e is irrational, that pi squared is irrational, that the cosine of any non-zero fraction is irrational. The trap is reusable. What makes it beautiful is not that it is clever for its own sake. It is that a number whose digits refuse to repeat forever is pinned down completely by a hump, a sum, and a single area caught where no whole number can live. Pi keeps its endless, patternless decimal. Now we know for certain that no fraction will ever catch it.